while measuring the difference in current flow through the two hot lines and comparing it to the neutral current can indicate an open neutral. It's not a foolproof method. For example, if the load is balanced, the current flow through the two hot lines will be equal, and there will be no difference to compare to the neutral current. Additionally, some types of loads, such as motors, can cause current harmonics, which can make it difficult to accurately measure the current flow. As a result, relying on this method alone to detect an open neutral is not recommended. A more reliable way to detect an open neutral is to use a voltage meter to measure the voltage between the neutral and ground. If the voltage is greater than a few volts, this indicates that the neutral is open. A normal voltage reading between neutral and ground should be very low, ideally close to 0 volts. A significant voltage reading, like anything above 2 or 3 volts, suggests a potential problem with the neutral connection. This voltage appears because the neutral conductor, when open, can no longer effectively provide a return path for current, leading to voltage difference between it and the grounded parts of the system. Another way to detect an open neutral is to use a continuity tester to check for continuity between the neutral and ground. If there is no continuity, this indicates that the neutral is open. Continuity refers to a complete and uninterrupted path for electrical current. When the neutral is properly connected to ground at the service entrance, a continuity tester should indicate a continuous path between these 2 points. The absence of continuity suggests a break or disconnection in the neutral conductor, preventing it from fulfilling its grounding function. There are also commercially available devices that can be used to detect open neutrals. These devices typically use a combination of voltage and current measurements to determine if the neutral is open. While these devices can be more expensive than the methods described above, they are more reliable and can be used to detect open neutrals even in balanced loads and in the presence of current harmonics. These advanced devices often incorporate sophisticated algorithms and circuitry to analyze voltage and current patterns, allowing them to identify open neutrals under a wider range of operating conditions. They may also include features such as data logging and remote monitoring, which can be useful for troubleshooting intermittent problems. To further understand the complexities of open neutrals, it's important to consider the role of the neutral conductor in a standard electrical system. The neutral conductor serves as the return path for current from electrical loads back to the source. In a properly functioning system, the neutral conductor carries the imbalance of current between the hot conductors. For example, in a 120/240 volt split-phase system, if one hot leg is carrying 10 amps and the other is carrying 8 amps, the neutral conductor will carry 2 amps. The neutral is also bonded to ground at the service entrance, providing a low impedance path for fault current to return to the source, facilitating the operation of overcurrent protective devices like circuit breakers or fuses. An open neutral disrupts this carefully engineered system. When the neutral conductor is open or disconnected, the return path for current is compromised. This can lead to a variety of problems, including elevated voltages on some circuits, reduced voltages on others, and increased risk of electric shock. In the case of unbalanced loads, an open neutral can cause the voltage on one leg to rise significantly above 120 volts, while the voltage on the other leg drops below 120 volts. This voltage imbalance can damage sensitive electronic equipment and create a fire hazard. Furthermore, an open neutral can prevent ground fault circuit interrupters or GFCIs from operating properly. GFCIs work by detecting small imbalances in current between the hot and neutral conductors. When an open neutral is present, the GFCI may not be able to detect a ground fault, leaving people vulnerable to electric shock. The National Electrical Code, or NEC, provides specific requirements for the installation and grounding of neutral conductors. These requirements are designed to minimize the risk of open neutrals and ensure the safe operation of electrical systems. It's crucial to adhere to these requirements when installing or modifying electrical systems. Regular inspection and testing of electrical systems can help to identify potential problems with neutral conductors before they lead to more serious issues. Some common causes of open neutrals include loose connections, corroded conductors, and damage from rodents or other pests. It's important to address these issues promptly to prevent open neutrals from occurring. When troubleshooting an open neutral, it's essential to follow safe electrical work practices. Always to energize the circuit before working on any electrical components. Use appropriate personal protective equipment, such as insulated gloves and safety glasses. If you're not comfortable working with electricity, it's best to call a qualified electrician. The location of the open neutral can sometimes be difficult to pinpoint. It could be at the service entrance, in a junction box, or even inside an electrical appliance. Start by visually inspecting all accessible connections and conductors for signs of damage or corrosion. Use a voltage meter and a continuity tester to systematically check the neutral conductor for continuity and voltage drop. Pay close attention to any areas where the neutral conductor is spliced or connected to other components. If you suspect that the open neutral is located inside an electrical appliance, disconnect the appliance from the circuit before attempting to troubleshoot it. In some cases, it may be necessary to disassemble the appliance to access the neutral conductor. Be sure to follow the manufacturer's instructions when disassembling and reassembling electrical appliances. Remember that working with electricity can be dangerous. If you're not sure what you're doing, it's best to call a qualified electrician. Always prioritize safety when working with electrical systems. An open neutral can create a dangerous situation, so it's important to address it promptly and effectively. By understanding the principles of neutral conductor operation and the methods for detecting open neutrals, you can help to ensure the safety and reliability of electrical systems. Moreover, the suggestion to adapt GFCI technology to detect open neutrals is interesting but presents challenges. Standard GFCIs detect current imbalances between the hot and neutral conductors, typically around 5 mA. They are designed to trip quickly, within milliseconds, to protect people from electric shock. Adapting this technology to detect open neutrals would require a different approach. An open neutral doesn't necessarily cause a current imbalance between the hot and neutral conductors. Instead, it disrupts the voltage balance and can cause elevated voltages on some circuits. Therefore, a device designed to detect open neutrals would need to monitor voltage levels and respond to deviations from the normal voltage range. One possible approach would be to create a device that monitors the voltage on each leg of a 120/240 volt split-phase system. If the voltage on either leg deviates significantly from 120 volts, the device could trip, disconnecting the circuit. The trip point would need to be set high enough to avoid nuisance trips due to normal voltage fluctuations, but low enough to protect against damage from overvoltage conditions. Another challenge is that open neutrals can be intermittent. A loose connection, for example, might cause the neutral to open and close sporadically. A device designed to detect open neutrals would need to be able to respond quickly to these intermittent conditions. It might also need to include a time delay to prevent nuisance trips caused by brief voltage fluctuations. Furthermore, the device would need to be able to distinguish between an open neutral and other types of electrical faults, such as short circuits or ground faults. This would require sophisticated circuitry and algorithms to analyze the voltage and current patterns on the circuit. While adapting GFCI technology to detect open neutrals is technically feasible, it would likely be more complex and expensive than standard GFCIs. It would also require careful consideration of the trip point, time delay, and fault discrimination capabilities. Additionally, such a device would need to meet rigorous safety standards to ensure that it does not create a fire hazard or increase the risk of electric shock. The NEC addresses open neutrals through various requirements related to grounding and bonding. Section 250.24 C discusses the grounding electrode conductor connection to the neutral conductor at the service equipment. This ensures a low impedance path for fault current and helps stabilize the neutral voltage. Section 250.50 covers grounding electrode systems, emphasizing the need for a comprehensive grounding system to minimize voltage fluctuations and provide a safe path for fault current. Section 300.13 B mandates that the continuity of the neutral conductor shall not depend on device connections, meaning that the neutral must remain continuous even if a device is removed from the circuit. These code requirements aim to prevent open neutrals and mitigate their effects. In summary, detecting open neutrals requires a multifaceted approach. While measuring current differences has limitations, voltage measurements, continuity tests, and specialized devices offer a more reliable detection. Adapting GFCI technology is a possibility, but it presents significant engineering challenges. Adhering to NEC requirements and implementing regular inspection and testing programs are essential for preventing and addressing open neutrals in electrical systems. Remember to always consult with a qualified electrician for any electrical work to ensure safety and compliance with applicable codes and standards.